This is the second video of atomic structure and periodicity. We are going to cover the periodicity topic in this one. We're going to start with ionization energies. Well, this particular bit is technically part of the atomic structure in the specification, but because it's repeated in both sections, in periodicity and atomic structure, I'm going to cover it in this video. So what is ionization energy? When we think of ionization energy, we need to first revise very quickly the electronic structure. Now, this line in here shows ionization energy. If you remember, for electron configurations, you have increasing energy sublevels, 1s, 2s, 2p, 3s, 3p, 3d, and so on, right? So 1s is the lowest energy level, 4f in this case, from the ones that we've shown, is the highest energy level. You remember these two are sort of in the different order. So what is ionization energy? Ionization energy is energy needed to remove an electron from a certain sublevel, right? So for example, if I've got an electron here that needs to be removed, it needs to have this amount of energy to be removed. But at the moment, this is the amount of energy that this electron has. So this is how much it has already, but it needs to be here to be removed. So if I want to remove this electron, this is the amount of energy that I'm going to have to add, okay? And that is going to be our ionization energy, is the amount of energy is needed to add to an electron to be removed from that. You need to know the particular definition. So this was an explanation, but now a definition for you to note down and to memorize for exam questions. So ionization energy, sometimes written as IE, is the energy needed to remove 1 mole of electrons from a mole of atoms in the gaseous state. Underlined because often you lose a mark if you don't include that section. Now, there's an equation for ionization energy. So we can show in an equation, think of it like a half equation. It's very similar to a half equation, but there's some differences. So you're starting, per us in a definition, we're starting from a mole of atoms. So for example, if we have element X, this is the mole of atoms, but it's in the gaseous state, so you must have G. And it turns into a positive ion, 1+, because you're losing 1 electron. It has to be in a gaseous state, and plus 1 electron has been removed. Okay, so this is equation for ionization, for the first ionization energy, when your first electron has been removed. You can have then the second ionization energy when the second electron is removed, and so on and so on. So a few exam tips. When you're asked to define ionization energy, you need to give this definition and don't forget the gaseous state bit. If you asked for example, write an equation for first ionization energy of sodium, you need to make sure to remember about these gas symbols. So the easier it is to remove the electron, the lower the ionization energy, right? Does that make sense? Because our ionization energy is the amount of energy we need to put in to remove the electron. The less energy we need to put in, the easier it is to remove the electron. So ionization energy depends on many factors. So have a quick look at this diagram to help you. Can you think of factors? There are 3. Pause. Okay, so the first factor is distance from the nucleus. If I have an electron close to the nucleus, it's going to have more attraction to the nucleus. So if I have an electron from here, it's going to be needing more energy to remove the electron. If I have an electron further out, it's going to be easier to remove it. Less energy is going to be needed. Nuclear charge. So if that nucleus is 5+, comparing to another nucleus, which is, let's say, 20+, but we keep all the other things the same, so electron is from the same distance, which one is going to have higher ionization energy? The one with 20+, because 20+ is more positive charge, it will have more attraction to the electron than 5+. So if I have higher nuclear charge, I will have higher ionization energy because I will need to provide more energy to overcome the higher attraction from the nucleus. And the third one is called shielding. Shielding is repulsion by electrons, because if I'm looking at this electron in here, it's not just nucleus here and electron in here. There's other shells in here with all sorts of electrons on these shells. So these guys, that's your shielding. Now, what they do, they repel this electron. So the more shielding I have, the more this electron is repelled, the easier it's going to be to lose it, the lower the ionization energy. So the closer the electron is to the nucleus, the higher the attraction between the electron and the nucleus, the greater the ionization energy. And the same idea with the lower the nuclear charge, the higher the nuclear charge, the greater the ionization energy. The less shielding, greater ionization energy. You need to understand these factors and be able to compare them for all sorts of different, situations. So feel free to pause it and note it down, and then we're moving on. Right, so ionization energy, there's more than one ionization energy. The first ionization energy is energy required to remove the first electron, right? Now, then the second ionization energy, you're removing the second electron, not both. So look at this comparison. This is my first ionization energy. So you're starting from 0 charge to +1 charge, and you're removing 1 electron. Your second ionization energy, you start with +1, you make a +2, and your second electron is removed. So here, first electron is removed. Here, second electron is removed. Now, third ionization energy, and so on and so on. So be very careful. Sometimes people confuse it and think second ionization energy is we remove 2 electrons. No, we remove second electron after the first one is already gone. So don't make that mistake. Right, so what I want you to do, just to quickly revise that, is can you have a go and write an equation for ionization energy for sodium, first ionization energy, second ionization, third ionization energy. Pause. Right, let's check. So you can see we're starting from 0 charge. It's become a +1 charge because we lost our first electron. It's first ionization energy, so we lost our first electron. In my second ionization energy, I'm starting from +1 because I already lost the first electron, and I make a +2, and this is my second lost electron. And here we've got our third lost electron, and we go from +2 to +3. Okay, so these values have been measured, and these are the values for first, second, and the third ionization energy. What can you tell me about these values? So you can see that the successive ionization energies increase, right? So it's easiest to remove the first electron, and then a bit harder to remove the second electron, and harder to remove the third electron. Okay. Now another thing. So think of it, why do you think that is? And then the second question, how much energy do we need for the following change? Okay, so if I want the energy to remove 3 electrons, so this is first ionization energy plus second ionization energy plus third ionization energy. I need to add these 3 numbers because we removed these 3 electrons. So we add, there's a sum, symbol of the sum. So these 3 numbers, you would need to add them up. I can't be bothered to do that now, to get the answer for that second question. Now, what about the first question? Why successive ionization energies increase? So this is the the electron configuration of sodium. You can see 1s2, 2s2, 2p6, 3s1. Which electron is going to go first? Well, we're going to start with the highest energy level. So this is my 3s electron, right? So 3s electron. So if I have nucleus here, okay, this is the furthest out. So the distance is the highest, right? And it's got the most shielding because it's got 1s, 2s, and 2p in between. So here we've got higher distance and high shielding. So high distance and high shielding makes the ionization energy small, right? Which electron is lost in here then? Well, it's going to be one of the 2p electrons. And the next electron is going to be another one of the 2p electrons, right? So these are going to have some similarity. That's why you can see that this is 400 something, like almost 500, and this is like 4,500, so it's like 9 times bigger. So you have, because these are on the 2p. Now you can see that this one, well, both of them will have one thing in common. They've got lower distance, so shorter distance to the nucleus, and slightly less shielding, right? A bit less shielding. That's why, yeah, that's why. Now, in this case, nuclear charge stays the same, because they, in each case, they're sodiums, isn't it? So nuclear charge stays the same, so that's not a factor. Nuclear charge will be important when we compare different elements. When it's the same element, nuclear charge stays the same. Okay, so that's why this one has got lower distance and less shielding, so ionization energy is higher. And you can see that it's easier to remove the second than the third electron. Well, the second electron, you've got that extra repulsion in here because we're removing from a paired orbital. So this one has extra repulsion that makes it easier to remove. Yeah. Now, but however, it will keep on getting harder. These ionization energies are going to increase and increase and increase. And especially, it's harder to remove an electron from something that's positive. Yeah, so it's always the easiest to do the first ionization energy. Okay, let's move on. Right, so why do you need to know all of this? What's the point? Well, successive ionization energy values, so first, second, third, and so on, they can give us evidence on how electrons are arranged in energy levels and sublevels. We already sort of mentioned that. And you will need to be able to explain that based on data, what information we get. So you can see what is the trend, exam question, describe the first ionization energy trend down the group. How would you describe this trend? You can see that the ionization energies decrease down the group. Why do you think this happens? What's the reason? Okay, you thought that through. Let's have a look. So, so what happens is your nuclear charge increases as you go down the group because beryllium, magnesium, calcium, strontium, barium, and so on. Your nuclear charge increasing. However, the atomic radius increases as well because as you go down the group, you start with one shell, then you've got 2 shells, then you've got 3 shells. So you can see this distance, the radius gets bigger. The radius of the atom gets bigger, yeah, as you go down the group. Now, also that means more shielding because in here, you only have 1 shell here. That shell in the middle provides extra repulsion. Here, 2 shells in the middle provide extra repulsion and so on. Now, so on balance, you can see these 3 factors. On balance, it's always actually the radius that takes precedence. It's always the most important factor. So altogether, even though the nuclear charge increases in the group, however, the radius also increases, and that's a bigger factor. And we get more shielding. So in both cases, that means there's a weaker attraction as you go down the group from nucleus to the outer electron, and ionization energies decrease. Now, this is evidence for shells because we can see that the fact that we know the fact that electrons are on shells, some main energy levels, right? We're using here the GCSE model that you know from GCSEs. So that fact explains why the ionization energy decreases as you go down the group. So this is evidence for shells. You need to be able to recall this information and this reasoning to explain. They could say, I don't know, 4-mark question, probably not a 6-marker. Describe and explain the trend of first ionization energy down the group. Or they could say, explain how information about first ionization energy can give us evidence for shells or main energy levels in atoms. So you can use that. Now, so what about across the period? So here we go across the period. So we've got group 1 sodium, and group 2 magnesium, group 3, group 4, group 5, 6, 7. What happens? There's two things in here. So one thing is the general trend. What is the general trend? Yes, you can see that that's the general trend. The general trend is the increase, right? And then we need to think about why, and that's, I'm going to explain that in a second. Think of the factors that we were talking about. And then you can see there's some exceptions. So you've got here group 3 and here group 6. So these seem to be anomalous. They don't follow the trend. Right, they're not anomalous. There are reasons why they don't follow the trend. We're going to talk about that as well. So, do we know why the general trend, let's focus on that first, is an increase? So, as you go across the period, each time you're adding one more proton, right? Because that's how it works. So, you're adding one more proton, that increases the nuclear charge. Now, you get also a little bit more shielding, because each time you're adding one extra electron, each extra electron is more repulsion. So what about the atomic radius? What happens when you go across the period? So this is your period. What happens to atomic radius? We know that when we go down the group, the atomic radius increases. Down the group, the atomic radius increases. But what about across the period? We fill each new electron fills up the same main shell, right? Main energy level. So this is something quite good. So have a look in here. These circles represent the size of an atom. So you can see this is period 3 elements here. Period 3 elements, and that represents the size of an atom. What happens to the size of an atom across the period? It decreases. Right, you can see the values in here as well, decreases. Why would that be? Well, what you can see in here, there's nuclear charge listed here. So nuclear charge increases, right? Nuclear charge increases, but your distance, you always go under the same shell. So your distance doesn't change that much. So because you get each element, you've got an extra positive and an extra negative, an extra electron, extra atom, there's more attraction. So your attraction between, always say between what? Don't say just attraction increases. Attraction between what? Between cats and dogs? I don't know. So attraction between nucleus and outer electron increases. Why? Because nuclear charge goes up and you get more electrons every single time. So because attraction increases, what that does, it makes the size of an atom a little bit smaller every single time. And that is something that you will need to know. And that explains the trend, the general trend of ionization energies, right? So atomic radius decreases. So do you remember the general trend was up across the period, isn't it? So you get increased nuclear charge, you get more shielding, and you get smaller radius. All of these factors means that the strong attraction from nucleus to the outer electron, and as you go across the period, the first ionization energies increase. Very common question is, state and explain the trend of first ionization energy across the period. State, this is this bit, and explain is this bit. So they could say, state and explain the general trend of ionization energies across the period. You say first ionization energies increase. Reasons, because we've got increased nuclear charge, more shielding, atomic radius decreases, so strong attraction from nucleus to the outer electron. That's a full answer. Now we're going to have a look at the exceptions to the trend. So we had a look at the general trend, and now we're going to have a look at the exceptions. To look at the exceptions, we need to look at how electrons are laid out in subshells. So we're not just looking at the main energy levels, but subshells. So let's have a look. For sodium, the electron that goes on is the furthest out electron is 3s1. For magnesium is 3s2. For aluminium is 3p1. So what can you notice? Right, so the dip happens when we go from the S to the P. And this can be explained if you have a look, or something got moved in here. If you have a look at our diagram here, we've got energy over here. This is the complete removal. So the ionization energy to remove the 3p electron would be from the 3p level to where the complete removal happens, right? For the magnesium, it would be, sorry, something got shifted in here. I need to fix that later. So the amount of energy for the 3s would be this much, because 3s has got lower energy and 3p has got already higher energy. So 3p has higher energy, so needs a bit less to be removed. 3s is a bit lower energy, so need a bit more to be added to be removed. So this explains that. How do you write that when you ask the question? So the question could be, explain why going from magnesium to aluminium, ionization energy goes down or decreases, which is different than the general trend. To say that the electron that is lost from aluminium goes from 3p orbital. The electron that is lost from magnesium goes from 3s orbital. Now, I bolded this because you need to actually say from which orbital. You can't just say from p orbital, from s orbital. That's not going to give you full marks. You need to say from which specific orbital is lost. Then you say, well, 3p orbital is higher energy than 3s, so it's easier to lose electron. Ionization energy is lower. That's a full answer. Now, one thing to note down, because this is across the period, my example is period 3. This works for every period. So every period, whether you're looking at period 1, period 2, well, period 1 doesn't apply. Period 2, period 3, 4, 5, and so on, they all will follow the same trend. But instead of magnesium and aluminium, it will be whatever other element in group 2 and group 3. So that's one exception sorted out. So we keep going, and then there's going to be another exception in a second. So then silicon is 3p2. So now it's within p, yeah? So we continue following the trend because we are always on p. However, at 3p4, we've got a little bit of a dip. Not as much of a dip as in here, just a bit of a dip. Why do you think that is? Well, let's have a little look. So this is your phosphorus here at the top, and this is your sulfur at the bottom. Look, compare the 3p orbitals. Okay, so what happens in here is in sulfur, one of the 3p orbitals, they've decided to draw on this one, could have been this one. One of them has 2 electrons. This one, each electron is unpaired, but this one's got an extra electron that is paired. Now, what that means, there's additional repulsion, right? So sulfur loses electrons. Your answer to this question would be, sulfur loses electrons from orbital with 2 electrons, and you need to quote which specific orbital it is. It's a 3p orbital. And phosphorus loses electron from an orbital that only has 1 electron. Now, extra electron-electron repulsion makes it easier to lose electron from 3p4 than from 3p3. That's your full answer to this kind of question. And again, this works for period 2, period 4, does not just period 3, but the example, the names of the specific elements will be different. And instead of 3p, you will have like 2p. But always make sure that you quote this specific configuration that you're talking about. Okay, move on. So when you look at that pattern, we looked at what happens across the period. So you can see this is period 1 in here. This is period 2 in here. It's period 3 in here. That's the one that we just discussed, and so on. So if you go across the period and down the group, you've got this kind of repeated pattern. So if I split that just before, it's a group 1 metal, isn't it? Lithium, sodium, potassium, to remember the reactive metals. So this is your period 1, this is your period 2, period 3, and period 4, and so on, right? So what does that, what you can see is that this pattern corresponds to the main energy levels, isn't it? Yes, further main shell evidence. So this is the full picture, yeah, for the whole, well, not the whole periodic table, but for more elements. So you could see here, right, the first ionization energy go down, like down a group is decreasing. Yeah, as an example here is on group 0, but it's going to be the same for group 1, group 2, and so on. Then group 1, you can see there's also a general decrease. Okay. Now, what about across the period? The general trend across every period is ionization energy goes up, the general trend. And you can see that the exceptions would be analogous in each of these, isn't it? Yeah. So here you've got, here, yeah, this, you can see there's some information in this. Sorry. Now, you can also see that at the end of the period, you always have a big drop. At the end of the period, you always have a big drop. Why? Because it's always the hardest to get the electron out of a noble gas. But if I have group 1 metal, it's only got 1 electron on the outer shell. From here to here, the distance increases and you only have 1 electron. So it's a huge drop in ionization energy. It's a huge difference how much easier it is to remove an electron from group 1 metal than it is to a noble gas, isn't it? So if we look at, so this was first ionization energy for all of them, yeah, for all the different trends. Now we're going to move on from first ionization energy to looking at successive ionization energies. So when they talk about successive ionization energies, what does that mean? So that means first ionization energy, second, third, and so on. So we're looking at the same element and we take off first electron, second electron, third electron, fourth electron from the same atom, right? Until you've got no electron left, right? So this one had 11 electrons, right? And when you remove the first electron, that's the easiest to remove. Then as you remove the electrons, it always goes up, right? So every next electron is always harder to remove than the previous. But you can see a certain trend. This is on a logarithmic scale. You can see that there are 2 jumps in here. There's 1 jump in here, and there's 1 jump in here. Yeah, like these increase as well, but more gradually, right? But here you've got more steep jumps. So these correspond to the main shells, right? Because you can see on the first shell, we've got 2 electrons. On the second shell, we've got 8 electrons. And on the third shell, we've got 1 electron. And that corresponds to this, isn't it? So this is first shell, second shell, third shell, right? So on my third shell, I've got 1 electron. That's this, right? On my second shell, I've got these 8 electrons. That's this section in here. And on my first shell, I've got 2 electrons. That's this. So this provides evidence, yeah, on the information on the shells, how electrons are laid out in shells, right? So you can see the first electron is furthest away, it's easiest to remove, and then 8 electrons nearer to the nucleus, and 2 electrons very close to the nucleus that are hardest to remove, right? So if we change the scale on the y-axis, we'd be able to see also here the split into the 2s and 2p, but we're not doing that. So there could be further information to show the 2s and 2p. Now, so this is for the same atom, for sodium, information instead of a graph, the numbers. for successive ionization energies. If you just look at the numbers, you can see you've got 496, 4,563. There's a big jump in here. From here to here, so this is like 4,500, 7,000, 9.5, 13, 16, 20, 24, 28, 141. So you can see there's another big jump. Now, this kind of information, you will be asked in exam questions, and there's going to be one worksheet to do as well, where you need to find, you're given information about consecutive or successive ionization energies for an element. You're not going to be told what the element is, but you're meant to work out, for example, which group this element is. So if I have this and they don't tell me it's sodium, then I know that after the first and the second electron removed, I've got a big jump. It must be a group 1 electron, right? Because the big jump is always end of shell, right? Where new period starts. So if I ended my shell and then the next one is only 1 electron, that's group 1. If I had 2 numbers and then the next one would be a bit jump, that would be group 2, and so on and so on, right? So there's further practice on this in the successive ionization energies worksheet, and also there's more questions in this one, and I'll share with you the answers. So this is in your booklet. Well, we're going to move on. So we're going to look at classification of elements. This is relatively straightforward. So in your GCSEs, you might have, and in Key Stage 3, you learned about alkali metals. So alkaline metals being the group 1. So that's your group 1. The alkaline earth metals, do you know which ones they are? That's your group 2 metals. Transition metals, which are these guys in here, in the middle. You learned about, maybe, possibly, metalloids. So these are those gray ones in here. Or you could have heard of semi-metals, right? These blue ones are metals as well. So these are also metals. But they're like group 3 metals and so on. These are transition metals. So metalloids, or it could be semi-metals, is those gray ones on this diagram. Then we have lanthanides. Lanthanides are over here. Actinides are over here. They're normally shown at the bottom. In GCSEs, they weren't even shown in the periodic table. Now, what they really fit in here, that's where they come from. This group, sorry, this period and this period. However, if we were to put all of these 14 elements in here, that would make the periodic table much wider, and it would be more difficult to print it out on an A4. So they've been taken out and put down in here. Then we've got halogens, which are group 7, and noble gases, which are group 0, or sometimes you could hear group 8. And that's the older classification. Okay, so that's a revision from your GCSEs. Now, in your A-levels, we learned about SPD electron configuration. Based on that, we have S block elements, P block elements, and D block elements, and you can see them here shown. So what that depends on is where the highest energy electron goes. So if my highest energy electron, for example, for calcium, this is where calcium sits. Calcium's highest energy electron is in the 4s2, so that's an S block, right? But you don't need to work out the whole configuration. You can just find where the element sits. So group 1 and group 2 is S block plus hydrogen and helium. So group 1, 2, hydrogen and helium is S block. D block is all these transition metals in here that you're going to find out that actually not all the D block is the same as transition metals. There's some exceptions there, but that's later lesson year 13. And P block is all the elements in here. It's a common question. They could ask you, explain why calcium is considered to be S block element. Then you need to say that calcium's orbitals that have the highest energy electrons in are is an S orbital, 4s orbital. That means calcium is an S block element. They could say, identify which block iron belongs to, and explain why. So iron is over here, and you can see that the highest energy electrons are in the D, so it's a D block. Yeah, it's D, so it's a D block. Chlorine, the highest energy electrons are in P, so it's a P block. Helium is an S block. Right, so in GCSEs you learned some properties of elements depending on their group. So group 1 alkali metals, group 7 halogens, group 0 noble gases, and transition metals. You still need to know those. I'm going to very quickly revise them. So if you can be bothered, you can type in the YouTube video. This is the video of some of the reactivity of less common alkali metals. So group 1 elements, they react with other elements to get rid of the lone electron, the outer shell. That makes them obtain a full outer shell, which is the favorable configuration, noble gas configuration, right? So you know that from your GCSE, the outer electron is removed, you become a +1, and that is very easy to happen. Why is that? Because that one electron is got high distance from the nucleus, so it's very weakly held. Now, what happens to the reactivity of group 1 metals? It increases as you go down the group. Do you remember why? You pause and quickly jot down what do you think the reasons are, and then let's check. So as you go down the group, the atoms get larger, or you could say the atomic radius increases. So the outer electron gets further from the nucleus as you go down the group, so the distance increases. And the attraction between the nucleus and outer electron gets weaker as a consequence of that increase in size. So the electron is more easily lost, right? So this, you could explain that in the same way with ionization energy in A level, but in GCSEs, you didn't use that term. What about, so that's the, very quickly, alkaline metals reactions. Halogens. So halogens are non-metals and they have 7 electrons in the outer shell. They react with other elements by attracting and missing electrons. So again, to obtain a full outer shell. So they become a negative ion, a -1, because they accept an electron. Yeah, so they've got 7 altogether and they gain 1 electron from somewhere, for example, from that sodium that we saw before. Yeah, so what happens to the reactivity of group 7 elements? That decreases as you go down the group. So it's the opposite to group 1. What is the reason? Well, because in this case, we're not losing electrons. In this case, we're gaining electrons. So to gain electrons, you need to have stronger attraction. But as you go down the group, the atoms get larger, so the electrons get further away from the nucleus. So the attraction gets weaker, but we need the attraction to be stronger. Yeah, so if the attraction gets weaker down the group, it's more difficult to gain an electron, so the reactivity decreases. Noble gases, as you know that noble gases are inert, what do you think is the reason? Yes, so noble gases, they have full outer shell, so they do not lose or gain electrons, right? So they don't form ions. And they also, what is another way by which atoms can form bonds would be covalent bonds, sharing. So they don't need to share, they don't need to gain, they don't need to lose, they don't need anything, they're happy as they are. We will find out later in the year 13. There are some exceptions to that for some of the bigger noble gases, but these are very rare reactions and not that easy to perform anyway. So in general, noble gases are inert. Right, so this unit is called periodicity, but what really is periodicity? Periodicity is regular, periodic variation of elements with atomic number and position in the periodic table. So, for example, if we were talking about group 1 elements, right? So every period, a group 1 element would have similar reactions, right? They all group 1 elements, they all lose 1 electron, they all react with water, they all react with acids, and so on. So there's similarities, right? And then you have group 7, you've got the same story, fluorine, chlorine, bromine, iodine, they react similarly. Noble gases, they all similar to each other. So that's periodic variation. That means that across the period, the properties change, but they repeat themselves in the next period, right? That's why in one group, elements are similar to each other, but across the period, they properties change as you go along. Why do you think that is? Yeah, so we will need to look at the electron arrangements a little bit more to answer that question. So what I want you to do for all elements in period 3, I want you to write a simplified, so noble gas electron arrangements. Then I want you to decide which of them are S, which of them are P block. And then for each of them also to find out, are they metals, are they semi-metals, are they non-metals, are they noble gases? So pause and have a go. Right, so let's go through the answers for this. So for period 3 elements, these are their names. And then neon is the noble gas that comes before sodium. So we use the electron arrangement with neon, and then we've got 3s1, 3s2, 3s2, 3p1. So these two are S block because there's only S, but here we fill up P. So 3p1, 3p2, 3, 4, and 5. So these are P block, including noble gas is also a P block. And which ones are metals? So sodium, magnesium, aluminium are metal. Silicon is a semi-metal. Phosphorus, sulfur, and chlorine, they're non-metals. And argon is classified as a noble gas. So make sure you are able to classify all of these elements and do the configuration. So now we're going to have a look at physical properties of period 3 elements. And they are largely a consequence of some of what we just talked about. So we mentioned before the radius of an atom, right? And we said that across the period, the radius of an atom decreases, but we haven't really explained, well, how do we know that? How do you think we can measure the radius of an atom? Okay, so there's different ways depending if you're looking at the metallic, covalent, or ionic radius, but either way, you need to have 2 atoms next to each other to be able to determine the distance, because the part of the atom that is relatively easy by current standards of technology to detect is the nucleus. Nucleus has a high mass density and high charge density, so it's like a little target in there. Whereas the cloud of electrons in here, electrons are very small and they keep on moving around. You've got quantum mechanics kind of principles that are ruling this area. So we're not going to treat our atom like a ball and actually take the distance from the nucleus till the end of that ball, because that's not what an atom is. It's much more fuzzy than that. When you have a foggy day, can you exactly decide where the fog ends in which bit? It's all kind of like blurry, isn't it? So you can't do that. So what you do, you look at when 2 atoms are next to each other and you do the distance between the 2 nuclei and divide it by 2, and that's your atomic radius. Okay, so you either do it in a metal. So in the metal, you've got the atoms next to each other, and you can do that. I'm not going to go into the actual investigative methods. You can look it up. When you can do it when you have a covalent bond, so you can detect where the 2 nuclei are and divide the distance by 2. And you can also do that in an ionic substance, you know, like sodium chloride, for example, yeah, like magnesium oxide. You can get that distance sorted out. Okay, so why do you think argon is not included in this table below? Well, because all of these rely on bonding, isn't it? And what happens is that the argon is a noble gas. Noble gases traditionally, in general, they don't react. So we cannot have a metallic bond, covalent bond, or ionic bond to measure that distance between the 2 nuclei. What does the atomic radius depend on in an element? So it depends on, well, first of all, the number of shells. That's the main factor. Okay, then the second thing is the nuclear charge and the shielding and the distance of the outer shell to the nucleus, because that decides the strength of those 3 factors decide the strength of attraction, and they can mean that even if you have the same number of shells, my atomic radius shrinks. So down the group, the atomic radius would increase, but across the period, which this table shows, it would decrease. And how we can explain that trend is because of increasing nuclear charge. Okay, so across the period, the atomic radius decreases. Outer shell electrons are in the same shell, More protons in nucleus, same amount of shielding, or very similar. You could also say similar because really it's not exactly the same. Similar amount of shielding, so stronger attraction between nucleus and outer shell electrons, and that means the outer shell electrons gets pulled closer to the nucleus, which means the atomic radius decreases. So feel free to take notes. This is your usual state and explain exam question that you're required to know. Right, so quickly, what is ionization energy? What's the unit? And what does it mean, first ionization energy? So if you remember, energy required to remove 1 mole of electrons from a mole of atoms in the gaseous state. We haven't mentioned that before. What do you think is going to be the unit? But energy is in joules, so the usual unit that we have is kilojoules per mole. Why per mole? Because it says to remove 1 mole of electrons. That's why we need to have per mole. What about first ionization energy? The energy that's needed to remove first electron. Okay, first electron always needs the least energy to be removed, right? And we had this trend that we just discussed, and we had this trend as well that we just discussed. So these is something that you need to know. Right, so one new one that we haven't discussed in the previous section is electronegativity. Now, electronegativity we learn about in the bonding unit, and the definition for electronegativity is the power of an atom to attract the electron density in a covalent bond. So we've got a covalent bond in here between 2 fluorines or between hydrogen and oxygen, and that covalent bond has an attraction to the nuclei over there, right, in the atoms. So like for example, in here we've got 2 fluorines, but in here one is a hydrogen, one is an oxygen, so they're different than each other. So one of them may attract the this bonding pair of electrons more strongly than the other. I say electron density because it's more preferable than to say an electron or a pair of electrons. This always gives you marks. You say pair of electrons, it may apply 90% of the time, but not 10% of the time. So I prefer electron density that applies always. Right, so how does electronegativity trend relate to the period? So what happens across the period? The electronegativity increases. And we know that electronegativity is power of an atom to attract electron density in a covalent bond. So why do you think that is the trend? So pause, try to figure out. So as you go across the period, you get more protons, smaller radius, and that means it's a stronger attraction between the nucleus and the covalent bond electrons. So stronger attraction means higher electronegativity. This is typical exam style question. State and explain the trend of electronegativity across a period. And you can see, and we will cover that in the bonding unit a little bit more. The general trend is electronegativity, here described by this number, generally increases with some small differences, but general trend is increasing across the period and also increasing up the group, right? Why? Do you remember? Because we're talking about here attracting electrons, right? To attract electrons, you will have to have a small radius, right? Small radius and hopefully high, small radius, and as high as possible atomic, nuclear charge. So like in here, in this period, this one's got the smallest radius and highest nuclear charge. But can you see there's no values in here for the noble gases? Why there's no values for noble gases? Because electronegativity is talking about covalent bond, and they don't form a covalent bond. They're not reactive. Right, so this is the trend in melting and boiling point across period 3. Boiling point is the black, melting point is the blue. Can you pause and try to figure out why this trend happens? Okay, so let's go through the explanation. You will have to know all the details that I discussed, except for the numbers. Any numbers you don't need to know. So you don't need to know like this one is 3000 something, but you need to know the shape of the curve. So let's have a little look. So we got up to here before in our discussions. So what a melting and boiling point depends in structure and bonding. And you know from your GCSEs that we've got 4 types of structures, and only 3 of them apply to elements, right? Because here we're only looking at elements. So ionic is not going to apply because it doesn't apply to elements. We're going to have giant metallic for sodium, magnesium, aluminium. Silicon is giant covalent or macromolecular. And phosphorus, sulfur, chlorine is simple molecules. And argon is atomic, which is very similar to simple molecules, except it doesn't have molecules, but it also has weak intermolecular forces. So do you remember here we've got a strong metallic bonding. Here we've got lots of strong covalent bonds. Here we've got intermolecular forces, which are weak in those 2. Right, so let's have a look at the trends. So you can see that generally the giant covalent has the highest value. So if you go in here, this is your giant covalent, lots of strong covalent bonds. Now, then what we have, the second highest is the metallic, but within the metallic, there's a certain trend, isn't it? As you go from sodium to magnesium to aluminium, they all have metallic bonding, but it increases. The strength of the metallic bonding increases. We're going to talk about it in a second. And you also can see that for these 3, phosphorus, sulfur, and chlorine, they're not sort of following any specific trend. Now, one thing that you'll need to remember is that phosphorus, sulfur, and chlorine, when they're elements, they're not PS and Cl, it's they P4, S8, and Cl2. Only Cl2 we use in equation as Cl2. The other ones we don't use in equations like this. If I want to burn sulfur, I'm not going to have S8 plus O2. I'm just going to have S plus O2. However, that's the structure itself. So you can see that this one has the heaviest molecule. Right? And it's got the heaviest molecule, so that means it's got the strongest intermolecular forces, so that means it's got the highest boiling point, melting point than all of them, because the heaviest molecules have always the strongest intermolecular forces. In the unit of bonding, we're going to explain why. Okay, and the same idea in here, the P4 will be heavier than Cl2, so will be the second one, and chlorine is the lightest of them all, so it will be the third in the trend. That's why these melting and boiling points follow that pattern. Okay, so let's quickly revise that. So we need to know what kind of structure or what kind of crystal each element has. So we know they all like this. And this is the explanations if you wanted to know down. So strong attraction between metal ions and delocalized electrons. Aluminium has higher melting boiling points than magnesium and magnesium higher than sodium. Why? Because there is higher charge, more delocalized electrons, and smaller ions. Because this becomes a +1, this becomes a +2, this becomes a +3. So this one has a +1 ion and 1 electron. This one's got +2 ion and 2 delocalized electrons. This one's got 3+ ion and 3 delocalized electrons. So that one, I've got 3 times as much attraction as that one, right? So that's why this trend goes up like this on that. And obviously smaller ions, because we go across the period, they get smaller. And so if you were to compare it like this, this is what the difference would be between sodium and magnesium. Can you see more electrons, much more electrons, and the atoms are 2+, and smaller radius, so more attraction. Here we've got more attraction because of those 3 factors. Okay, so what about giant covalent? You have to break many strong covalent bonds, so that's why it's the highest. So that's this one here. And then the simple molecular, we've got weak van der Waals forces. So van der Waals force is a type of intermolecular force. We're going to learn more about them in the bonding unit, but you can start getting used to that word. For the purpose of this particular statement, you can just treat that as intermolecular forces. Okay, and S8 would have the largest, and P4 the second, and chlorine Cl2 the smallest. Why? Because that's the bigger molecule. The biggest molecule is called, or the heaviest, it's got the most electrons, so the highest intermolecular forces, of van der Waals forces. And this one is monoatomic, very weak intermolecular forces of van der Waals forces between atoms. So further practice for this unit is in the booklet, and I will make the mark schemes available.